Hi students, this is Mr. Bob. In this video, I'm going to be walking through two sample problems where we're going to apply the concepts of kinematics, the kinematics equations, and the DGUESS method. So the learning target is I can apply the DGUESS method and kinematics equations to analyze complex situations. Let's get right into it. Let's start with problem 1. Here you have sample problem 1. It says, a thorns player starts from rest and accelerates uniformly at 3.0 meters per second over a distance of 10.0 meters. What is her velocity at the 10.0 meter point? Use DGUESS. Notice on the right here, I've got my kinematics equations that we're going to refer to. And notice on the left here, I have laid out sort of DGUESS. So remember, the first letter D stands for drawing. What we learned in the last video is that for kinematics equations, it's really important to draw a quick picture, which, notice I've got stick figure person here, thorns player. And then it's really important to have a set of axes. And notice I've set up a set of axes, and I'm just going to mark the thorns player starting at the origin. That's always a good place. And I'm going to mark to the right is positive, to the left is negative. Okay, so there you go. I've got my sketch, and I know they're going to be moving in this direction, like so. Okay, the givens. To figure out the givens, I'm going to make that table that I talked about in the last video, which is the displacement Vivat sort of table. And now I'm going to read the problem carefully and figure out which information I have. So a thorns player starts from rest. From rest, what does that mean? From rest means that my initial velocity is 0. And accelerates uniformly. Okay, that word uniformly is important because that tells me that the acceleration is constant, and therefore I can use these constant acceleration equations. At 3.0 meters per second. What is that? That is my acceleration. I can write it this way, meters per second squared if I want to. Over a distance of 10.0 meters. What's that? That sounds like my displacement. So my displacement is a positive 10.0 meters. And then the question is, what is her velocity at the 10 meter point? So what is my unknown? My unknown is what is the final velocity. So notice I have 3 pieces of information and I have 1 unknown. So now as I move to the E, which stands for equation, I'm going to look over here, and with the equations, I'm going to try and figure out which of these equations incorporates the 3 pieces of information that I know and the unknown, the final velocity, and doesn't ask me for the time. Okay, so if I have time in these equations over here, I really can't use them. So I'm going to mark out this one. Nope, that has time, that has time, that has time. This one looks like the most promising. Let's just make sure. Do I know final velocity? This is what I'm looking for. Do I know initial velocity? Yes, check. Do I know acceleration? Check. And do I know displacement? Check. So notice I have all of the known, I know all the variables except for the one I'm looking for. So that is the one I want to use. So I'll write it over here. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So I'm going to solve for the final velocity. And in this case, it's kind of easy because all I have to do is just take the square root of both sides. So I'll do that here, square root, and my solution is final velocity equals the square root of the initial velocity squared plus 2 times the acceleration times the displacement. Now I'm down here to my last step, which is to substitute. So I'm going to substitute in those values. Square root of, this is 0 plus 2 times 3.0 times 10.0. And so 2 times 3 times 10, that's going to be 60. So the square root of 60. And it's always good to estimate answers before you put them in your calculator. So I know the square root of 64 is 8, and the square root of 49 is 7. So it's going to be somewhere between 7 and 8. It's probably going to be closer to 8 than 7. So it's probably going to be somewhere around 7.7 meters per second. That would be my guess. So I'm going to do it quickly here in my calculator. And the answer I get is 7.7 meters per second. Okay, so that's sample problem 1. Notice we've gone through all the steps, the DGUESS, to get our solution. Let's move on to sample problem 2. Sample problem 2 says a car initially traveling at 7.0 meters per second uniformly speeds up for 4.0 seconds at a rate of 5.0 meters per second squared. How far does it travel in those 4.0 seconds? Use DGUESS. All right, here we go. Let's begin with our drawing again. Take our little car here. Notice my car. It is the most awesome looking car in the world. Boom. Set up my coordinate system, which again is so important. 9 times out of 10, it's best to start the object at the origin, makes things easier for you. And notice I'm going to say to the right is positive, to the left is negative. Okay, again, I could have set it up the other way, but I'm trying to do it in a way that kind of makes it easier for me in terms of having to deal with less negatives. So now I'm on to the givens. So a car initially traveling at 7.0 meters per second. Oh, okay, initially traveling. That suggests that the initial velocity was 7.0 meters per second. Uniformly speeds up. Okay, uniformly speeds up. What does that mean? That means, ooh, constant acceleration. Good, it's good because that's important. So I'm just going to write constant acceleration. For 4.0 seconds, looks like I have a time here, change in time, at a rate of 5.0 meters per second squared. That's an acceleration. How far does it travel in those 4.0 seconds? Looks like I'm looking for displacement. So notice again, I have 3 givens, 3 things I know. I have 1 unknown. And so again, I go over here to my equations and I want to figure out which of these equations is going to work for me. I'm looking over here. I don't know final velocity, so I want to rule out any equations that have final velocity in them. So no, and no, and no. So by process elimination, that second equation looks promising, but let's just make sure. I know the time, check. I know the acceleration, check. I know the initial velocity, I know the time, and I'm looking for the displacement. So there you go. So the equation I'm going to use is that the displacement is equal to the initial velocity times the time plus 1/2 times the acceleration times time squared. So the solve step here is quite straightforward because I've already solved for displacement. By the way, in the future, they won't quite be so straightforward. You will have to do some significant algebraic steps. But we can basically come all the way down here to the substitute, which then we do initial velocity times the time plus 1/2 times the acceleration times time squared. And so I get 28 in this term. This is 16 divided by 2 is 8, and this is 40 if I'm doing this correctly. So 68 meters. So we could say the car traveled 68 meters. Okay, and it's always good actually, car traveled 68.0 meters. It's always good to kind of phrase your answer in the form of a sentence. Okay, so these are 2 sample problems that should help you kind of get a sense for what the DGUESS method is about and how you use it to apply it to kinematics situations. I hope you've enjoyed this video. Have a good day.